So which of the following frequencies corresponds to the longest wavelength? Now remember, wavelength and frequency are inverses. So longest wavelength means the lowest frequency. So whichever one of these frequencies is the lowest will have the longest wavelength, which that would be 10 to the 5th, which is B. All right, moving on. So which of the following is not determined by the principal quantum number n of the electron in a hydrogen atom? So n is the principal energy level. So which one is not determined by it? The energy of the electron, obviously that's determined because we have the equation from the Bohr model. So that's not the answer. The minimum wavelength of the light needed to remove an electron from the atom. So the minimum wavelength can also tell the minimum frequency, which can tell us the energy, which again, we know the energy from the principal quantum number. The shape of the corresponding atomic orbital. That isn't determined directly, but you can have some insight into it, because if it's a s orbital, p orbital, d orbital, f orbital, our principal quantum number doesn't tell us that exactly. And also the size of the corresponding orbital. So the size of the orbital, the size of the energy level is determined, but not exactly the size of the orbital. The shape of, this is a weird, I don't like this question, because C and D are technically correct, because the orbital, we don't need to know n to know what type of orbital is it, but n could help us kind of narrow it down. So the shape, and maybe that's why this question, I don't think this question was on the exam, but I would say the shape, because we don't really, because the size, probably the D, they meant to say the size of the size of the shell, but the size of the shell we can determine from n, but the shape of it, the shape of the subshell, or the shape of the orbital, we don't know from n. So that should be the most correct answer. But again, I don't like that question. Okay, next, how many electrons in an atom can have quantum numbers n equals 4, l equals 3? All right, so we can draw a tree diagram for that. So n equals 4, l equals 3. L equals 3 corresponds to F. So remember, L equals 0 is S, L equals 1 is P, L equals 2 is D, L equals 3 is F. So an F orbital, or an F subshell, can have 14 possible electrons. So 14 electrons is going to be your answer. And the way we figure out that 14 is going to be if we go from L to ML. The possible ML values are -3, -2, -1, 0, 1, 2, and 3. And in each one of those orbitals, we have a positive spin electron and a negative spin electron. So it'll be how many orbitals? 1, 2, 3, 4, 5, 6, 7 times 2 is going to be 14. So 14 is your answer. Next, which of the following sets of quantum number is incorrect? So we need to follow our rules. So our L needs to only be in the range of 0 to n minus 1. That's the range. So we cannot have n equals 3, L equals 3. L can only be a maximum of 2 if L equals 3. So this is incorrect. All right, now some Lewis structures. So which of the following describes the correct shape and polarity of XeF4? So xenon is a noble gas. It has 8 valence electrons. Fluorine only, so let's give you some cheat sheet here. If a molecule like this, if you have a halogen it's something with a halogen 2, halogen 3, like F2, F3, F4, F5, whatever it is, those halogens will all the time have a single bond to the central atom. Another follow-up question that a lot of you guys have: how do you know what's the central atom? What I tell my class, it's never hydrogen, it's always carbon, and it's always the one that has the least number of atoms in it. So, for example, XeF4, there's only one Xe and 4 Fs. It's going to be xenon. So, whichever one has the least amount. Usually that one is written first. So, and also if it's carbons there, then it's always going to be carbon. So fluorine it'll be 4 single bonds to fluorine. So there's 1 single bond, 2 single bond, 3 single bond, 4 single bond. So what's left over? We have 2 electron pairs. So these electron pairs will actually orient themselves in an arrangement where it is square planar. So one pair will be on the top, kind of like this, and the other pair will be on the bottom, and the F's will kind of be going like in a square, because they'll be on the same plane. So it's going to be nonpolar and square planar. And it's nonpolar because once it is in a square planar molecular geometry, the symmetry is equal. So it's important to know those. Your symmetry, know your molecular geometry and your electron geometries. And if you want to go on my YouTube channel, look up the chapter 11 overview video that goes through it really quickly. All right, which of the following ionic compounds is the highest melting point? Meaning, which one requires the most energy to break apart the bond? In other words, which bond is the strongest? So a strong bond means they're close together, small radius, and also a lot of charge. So +2, -2s, we're looking for something like that. So calcium sulfate, or calcium sulfide, it's a +2, -2. That's good. Strontium chloride, it's a +2 and a -1, not as good. Lithium oxide, same thing, not as good. Calcium oxide, pretty good. Calcium or sodium chloride, not good. +1, -1. So out of these, we have calcium is constant. Oxygen is smaller than sulfur because it's higher up on the table. If they're closer together, it's like calcium oxide, it's going to be stronger. So calcium oxide will have the highest melting point. All right, number 7. Which of the following species are paramagnetic? You have titanium, titanium 2+, and titanium 4+. So if we go to the periodic table, actually it's not on this. We don't have a periodic table here. But titanium is the titanium is 4, the valence electron is 4s2, 3d2. That is the valence electron configuration for titanium. So writing it out in an atomic orbital, we have 4s like that, and we have 3d, 1, 2, 3, 4, 5 like this, and it's like 1, 2. So which of the following species are paramagnetic? That means they do not have, that means there's at least one unpaired electron. That's what we mean by paramagnetic. So originally, off the start, titanium in the neutral state, it has 2 electrons that are unpaired. Therefore, titanium will be paramagnetic. 2+, if we take out 2 electrons, it will not be paramagnetic, it'll be diamagnetic. And then if we take out 4 electrons, so take out these 2, it will also be, well, actually, wait, I messed up. You know, I'll tell you why I messed up. Because titanium 2+, right? We know that titanium is paramagnetic. Titanium 2+, you are removing 2 valence electrons. Now, which ones are the valence electrons? Not 3d, because 3d is a lower principal energy level than 4s. So the 4s electrons will be removed first, like this. So yes, Ti2+ is going to be paramagnetic because these are unpaired. And then Ti4+, these would be removed and it'll be dimagnetic again because every electron on the lower energy levels will be they'll be paired up. So the answer would be C. Okay, next, number 8. So ethylene combusts in air to form CO2 and H2O, and we have a balanced reaction. Using the table given, what is the enthalpy change for the balanced reaction? Now, enthalpy change using the bond energies. Now, this is where some students get confused because when we went over enthalpy, we said that it was the products minus the reactants. Now, in this case, when we're talking about bond energy, it is reactants minus products. And the reason why, in short, is because the numbers are the opposite. So the enthalpy of formations are usually negative because forming a more stable compound releases energy. In this case, the energies will be positive. So doing the opposite operation, meaning reactant minus product, will give you the same answer. So just don't overthink it. That's basically what we're doing here. So it's usually what I tell my class, bonds broken minus bonds formed. So you have to figure out the Lewis structure for everything in order to know the bonds broken minus the bonds formed. So for C2H4, it's a C double bond C, and it looks like this. And then oxygen, we know is an O double bond O. These are the reactants. These are bonds broken. So what are the bonds broken here? We have obviously one of the OO bonds, OO double bonds, so that's 495, plus a C double bond C, which is 602, plus 1, 2, 3, 4. 4 times our CH, which is 413. This is your bonds broken minus bonds formed, which would be CO2. CO2 looks like this. And then H2O looks like this. So we have 2 C double bond O.
So 2 times 495 not be multiplied by 3?
495 will not. Oh, whoops, it would be. Correct. We have 3 of these. Thank you so much. So we have 3 of these. 3 times that. And then we have 2 CO2s. So this would actually be 2 times the 799 times another 2, because there's 2 CO2s, plus 2 times the waters. Now each water has 2 OH bonds. So it would actually be 4, meaning the 2 OH bonds, times the 2 H2Os themselves, times 467, like that. And then if you solve this, you'll get one of the answers. And one of you guys could try that out on your own. And you can see what you get. But yeah, so that's how you do it. It's bonds broken minus bonds formed. All right, you get negative 1325. Thank you so much. So the answer would be C. Awesome. All right, so what is the wavelength in meters of a photon that will excite an electron from n equals 2 to n equals 4? So basically, what is the energy, right? And we could figure that out. So the energy would be equal to negative 2.18 times 10 to the negative 18, I believe. And then we have, and it should say in a hydrogen atom, because normally it's hydrogen atom, it would be 1 over n final squared minus 1 over n initial squared, like that. So this is what we're trying to solve. We're going from n equals 2 to n equals 4. So the n, so it would be 1 over 4 squared minus 1 over 2 squared. Plug that in and you get the energy. This energy would be equal to nh nu. So we can figure out, or it could be, well, n is 1. So it would be hc over lambda, which lambda is the wavelength, and we can solve for the wavelength. So basically, if we plug both of those equations together, and I know I'm being a little bit lazy here, but this is, I just want to get the point across on how you're doing, how to do this. It would be h, which is your 6.626 times 10 to the negative 34, times the speed of light, which is 3 times 10 to the 8, divided by lambda, which you're finding, equals this, with n final being 4 and n initial being 2. Now, I saw that comment. Do we think that number 8 is actually B? Is that what some of you are getting? Okay, some people are getting 1300. So let's, yeah, C. We're getting mostly C. So we'll stick with that for now. And you got, maybe there's a mistake in the calculator or something. Okay. So if you guys want to try to solve 9 also, that's, yeah, tell me what you get for 9. Make you guys work. Oh, A. Nice. Thank you. Or E. Uh-oh. A or E? E. Okay, we have 2 E's. So let's go with the majority rules. A is the energy. Ah, so A is probably the energy. The answer key says B. All right, so okay, not what I hoped for. So, oh, for number 8. For number 8, well, the answer, I don't know. This is for number 8. This is right. Make sure to put this 3 times. 3 times 495 plus the 402 or the 602 plus plus
No, I'm looking back at my finals. Yours doesn't match. I mean, the questions are the same, the order is not. So I think maybe that kind of just threw it off.
Oh, okay. Yeah, because this is so don't look at the answer key for these because the numbers are not the same exact thing as the exam 3 because I couldn't find the actual raw copy of exam 3. This is just the question bank that we made exam 3 from. So the questions might not align. So let's go with C for number 8. Number 9, what do we have? Yeah, don't look at the answer. Don't look at the answer guide. Don't look at the answer guide. Okay. For number 9, do we have an answer? Okay, I'll leave it like this for now. E. All right, let's just say E. Yep, we have E. Okay. All right, cool. Thank you. Thank you for that. Makes my life a lot easier. All right. And for those of you who are watching on YouTube, you guys can try to figure that out. Just pause the video and try to solve it. Okay, next, formal charge. Now, the best way to find formal charge is you look at the valence electrons of the element. So let's go with oxygen. Let's go to the right oxygen. Valence electrons are 6 minus dots and so it's kind of rhymes. 6 minus dots and sticks. So to find formal charge is you're literally subtracting the dots and sticks. So in this case, for oxygen, 1, 2, 3, 4, 5, 6, 7. 6 minus 7 equals -1. That's the formal charge. For this carbon in the middle, 4 is the valence electrons minus 1, 2, 3, 4. 4 minus 4 is 0. So, right, dots and sticks. Oxygen for here, we have 6 minus 1, 2, 3, 4, 5 plus 1. So that's all it is. That's how you find out the formal charge. Now, what is the formal charge of the oxygen atoms in the molecule? Now, this is a stupid question. These are like raw questions because obviously we should number these oxygens because you don't know which one's asking for what. But we know that the top left one, let's see. So it's dots and 6. So 6 minus 1, 2, 3, 4, 5, 6. That's 0. So we have 0, -1, and +1. So that's probably the answer. Well, that's actually the answer. Yeah, that's the only combination that's correct. So, yep. Okay. So what is the hybridization and the structure of the indicated atom below? So we have a carbon which has 4 single bonds to it. So that what that means is it's sp3 hybridized. And we know that it is tetrahedral because it has 4 single bonds, 4 atomic groups attached to it. So it's tetrahedral. So A, sp3 and tetrahedral. Next, number 12, what is the frequency of a single photon with a mole if a mole of photons has a collective energy of 7946.4. Okay, so what we can do is we know that a mole of photons has that much energy. So we can do this 2 ways. We can take 7946.4 divided by Avogadro's number to figure out the energy, so E of E photon. We can take that E photon and we can say this equals H nu. And we can just find nu and find the frequency that way. So we find that E photon, this equals 6.626 times 10 to the -34 times our nu, and our nu would be the answer. So if you guys want to figure that out, that would be very helpful. And I'll give you guys a second to do that. D, nice. Thank you so much. D. Okay, moving on. So draw the Lewis structure for SO42-, which obeys the octet rule. What is the formal charge on the sulfur? So now normally, this SO42- may not obey the octet rule, but it's saying that we want to force it to obey the octet rule. So let's just start out with, wait, hold on. I did that wrong. So let's just start out with our sulfur, oxygen, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Oxygen, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then we have 2 more electrons we have to add. So let's just keep those in mind. So if we make single bonds with everything, I don't know why I did that. Let me erase that line. We make single bonds. Now, the sulfur has 2, 4, 6, 8, 9, 10 electrons. So what we can do, and we have 2 more electrons out here. So to obey the octet rule, we can get rid of these 2 electrons. And right at this point, each oxygen actually has 7. So we can just place one of those electrons on each of the oxygens. So each one will have 8. Like that. So at this point, this is the way that SO4 2- will obey the octet rule, because the sulfur will have 4 bonds, that's 8 electrons. Each oxygen will have 2 electrons in the bond, and then 1, 2, 3, 4, 5, 6. And each one will have 6 electrons in the outside and 2 in the bond. So everything has everything has 8 electrons. So for the sulfur in the middle, again, it's valence electrons minus bonds and sticks. There is no, or minus dots and sticks, sorry. So there's no dots and there's 4 sticks. So that's 6 minus 4 plus 2. So the answer would be C. All right, moving on. In which of the following molecules is the electron and molecular geometry the same? Another way of saying that, and again, I go over this in my chapter 11 overview video, is that which of the following does not have a lone pair of electrons? So H2O, we know it does, because our molecular geometry is bent and our electron geometry is tetrahedral, so that's not it. NH3, we have trigonal pyramidal, and we have tetrahedral for our electron. H2S, we have lone pairs, so it's going to be bent as well, similar to water. SO4, or SO2, we have lone pairs. So we have as 1, 2, 3, 4, 5, 6. We have 2, so we have 2 double bonds like that, and you're going to have 1 lone pair left over, and it'll be bent. For CO2, we don't have that. So CO2, we have no lone pairs on the central atom, and it's going to be linear. So the molecular and electron geometry will be linear. Next, draw the structure of methanol. What is the molecular geometry? Does the SO2 have resonance structures? So yes, it could, but this one's much more stable. So the resonance structures won't really play much of a role in, so it does, but that won't play a role in making the molecular and electron geometries the same. So that they'll still be different with those resonance structures. Because sulfur likes to have either 2, 4, or 6 bonds usually. So the resonance structures will kind of deviate from that a bit, making them less stable. All right, so draw the structure of methanol. So we have carbon in the middle, we have these hydrogens, then we have an oxygen with 2 lone pairs, then we have another hydrogen. What is the molecular and electron, or what is the molecular geometry around oxygen? So it's going to be just like water. We have 2 lone pairs, and then we have 2 bonds. So these bonds are going to be pushed down or repelled by the lone pairs, making it bent. So B. Which following atom will have the largest atomic radius? So we're looking for which one is more to the bottom left and of the periodic table. And I think that one will be cesium, I think. Look at that table. Yep, cesium. Yep, so cesium. So barium is right next to it, but it has 1 more electron. So that electron will actually disperse the effective nuclear charge and actually pull those electrons will be pulled in a little bit. Well, no, sorry, it will you increase a proton, so you increase the effective nuclear charge, so that those electrons will be pulled in a little bit more. But cesium will be the largest. All right, so what neutral element is described by the electron configuration? Why does it say Cr there? Maybe because that was the answer. So, oh, yes. So I think the answer wasn't here. Okay. So which neutral element is described by the electron configuration 4s1 3d5? So if you remember, this is an important concept. There are two exceptions to electron configuration. If you have 4s and 3d, and if you have a situation where it's 3d4, so 4s2 3d4 is the expected electron configuration for chromium, but this is less stable than 4s1 3d5. The reason is because our d subshell likes to have its 5 orbitals completely filled or half filled. This is a more stable arrangement. So to do that, we can take one of our 4s electrons and move it over here to make it like that, to make it 4s1 3d5. This is a more stable arrangement, and the answer would be chromium for this one. And the same is true for silver. So silver is our, copper. Copper is 3d9, so it likes to be 4s1 3d10 instead of 4s2 3d9. So that's another exception. All right, so which orbital allows electrons to be lowest in energy? So we're looking for low principal energy level, so that's 2, and also lowest in the hierarchy of SPDF. So that's 2s is going to be the lowest. Good, D. All right, complete the Lewis structure below by adding lone pairs and pi bonds to the neutral molecule. How many single and double bonds are there? All right, so this one, yeah, this one's the one that had to be edited because this was a carbon. This vertex is a carbon. And if you don't take orgo, you don't. In orgo, that's commonplace to not show the carbons, but we're not there yet. All right, so we want a double bond with this oxygen, 2 lone pairs, because we want oxygen to have 2 bonds and a 0 formal charge. This carbon, therefore, is happy. It has 4 bonds, so we don't need to add anything else to it. This carbon has 3 bonds. It needs 4, so it needs to make a double bond with this carbon. That makes this carbon have 4 bonds, so that's happy. So then we need to have a double bond here, and that's it. So we have 1, 2, 3 double bonds and 7 single bonds. Let's see if that's true. 1, 2, 3, 4, 5, 6, 7. Yep. So the answer is D or E. Good. All right, number 18. Which of the following have their valence electrons in the same shell? So we should look at a periodic table, have one up, on my phone. And what you would do for this is just look at the table and say that which one goes across in the same shell. So like which trio. So cesium is in 6A, bismuth is in 6, has 6p, and AT is also astenine is in 6p as well. So I think A would be the answer. Let's look at the other ones. Indium is in 4p. Lead's in 5p, so that's not correct. And then nitrogen is in a different level as arsenic, so that's not true. Argon and krypton are different, and then zinc and cadmium are different. So the answer is A. I like this test, it's quicker. All right, so how many of the following species are paramagnetic? All right, so this might take a little bit. So scandium, so SC. SC is located in, looking at my table now. Oh, it's in it's right next to calcium. So scandium, its electron configuration is 3s2, 4s2 3d1. Bromine is 4s2 3d10 4p5. Barium is, let's just put it as 6s2. And then selenium is 4s2 3d10. And then 4p6. Okay. So these are all the ground states I put. I didn't put the charges yet. So scandium, the ground state is 4s2 3d1. If it's a +3 charge, that means these two electrons are gone and the 3d electrons are gone. The whole shell is gone. So therefore, every other electron not included here is paired up. So that means cesium or scandium will not be paramagnetic. It'll be di. Bromium, or not bromium. Wow, that's a new element. So bromine, it's 4s2 3d10 4p5. So if we remove, so 4p5 looks like this: 1 2 3 4 5. If you remove one electron, or sorry, if you add an electron to make it bromium minus, it will have a completely filled p shell, and it'll be 4p6. That means it will not be dimagnetic or not be para, it'll be di. Dimagnetic, again, means that your electrons are all paired. Barium 2 plus, you have 6s2, you're removing those two. Again, that one will be dimagnetic. Selenium, you are doing nothing to it, and it's filled up already. No, it's not filled up already. You have P6. Wait, it's not P6. That's wrong. You have P4. This is P. It should be 4P4. So P4 looks like this: 1 2 3 4. So then selenium will be the only one that is paramagnetic. So the answer would be C1. All right, almost there. Number 20. Which of the following represents the change in electron configuration as associated with the first ionization of calcium? All right, so calcium is located in 4s2. That's the configuration for it. First ionization, it will become 4s1. So we have argon 4s2 to argon 4s1 plus an electron. So that's C. So these are the type of questions that you'll get in ACS. They'll be quicker, but they'll require the same amount of knowledge. So, and the reason why I'm going through them quicker is because I've been doing this for 6 years, right? So I know what it's asking already. But I mean, for you, you have to, if you really understand the concepts, they will be this quick. All right. So next, which ionization process requires the most energy? Okay. So if you remember, going from first ionization to second to third always increases energy. But if you try to take away an electron from a noble gas, it requires an insane amount of energy. So let's take a look. Selenium is right next to, on the left of bromine. So let's just take a look at, I'll write a little periodic table. Bromine, and then what comes after that is krypton. So if you take an electron away from selenium to make it selenium plus, you're going this way. That requires some amount of energy. Taking selenium plus and removing another one, that requires more energy. So automatically, selenium plus is the second ionization state of selenium requires more energy than the first, because as you have additional ionization steps, the energy always increases. For bromine, bromine has a higher ionization energy than selenium, so its first ionization will be rather difficult, but again, its second ionization will be even more difficult than selenium's second ionization. So that means bromine plus is going to be the highest ionization. It requires the most energy. And the reason why is because bromine has more protons. So it will hold on to those electrons tighter. So it'll give them up. It will require more energy to give them up. Okay, so using periodic trends, place the following bonds in order of increasing ionic character. This means the difference in electronegativity. Which one is the highest difference? So, and yes, I know these questions are different, but that's good. This is the word bank. This is the question bank that we made to make exam 3. I don't exactly have the raw exam 3. I just couldn't find it. I'm sure it's somewhere, but I couldn't find it. So it's still good. All right, so using the periodic trends in order of increasing ionic character. So silicon, so let's do this. So we'll draw a little periodic table again. So silicon, phosphorus, sulfur, chlorine, and then argon. So electronegativity increases going from bottom left to top right. So going across a period, you have an increasing electronegativity. So silicon and phosphorus, they're pretty close. Silicon and chlorine, they're pretty far. Silicon and sulfur, they're close. So the biggest difference will be silicon and chlorine. So silicon and chlorine will be the biggest. Silicon and sulfur will be in the middle. Silicon and phosphorus will be the lowest difference. So that's the order. All right. So use bond energies and provided to estimate delta H. And this is more of kind of like we saw with exam 2 with, well, with earlier in exam 3, I'm losing my mind here. With earlier in exam 3 where we have bonds broken minus bonds formed. So XeF2. Even if we don't draw all the lone pairs, we know that XeF2 is going to look like this. And then we have fluorine F2 is going to be like that. We have 2 of these. And then the product is going to be XeF, and then we have 6 Fs. So 1, 2, 3, 4, 5, 6. Okay, so if that's the case, then we can do our bonds broken minus bonds formed. So bonds broken, we have 2 XeF bonds. So 2 times 147 plus 2 times FF bonds, which is 159. And then this is going to be our bonds broken minus the bonds formed, which is pretty easy. It's just 6 times our XeF bonds. XeF, which is 147. Like that. So that'll be your answer. And to limit confusion, and this one's pretty simple, I'm going to solve it myself. 2 times 147 plus 358. That's not it. Nope. Wait. So 159 times 2 is 318. So 2 times 147 plus 318 is 612. 612 minus 6 times 147, that's 882. 612 minus 882 is negative 270, which is E. Okay, good. We're at the home stretch, so bear with me. So 24, identify the compound with the smallest dipole moment in the gas phase, meaning which one's the least polar? That's what smallest dipole means. H2 is pretty damn nonpolar, so that will have the smallest dipole. CLF will be pretty large. HF is very large. Ki large, and this one also has a dipole, so H2. H2 is extremely nonpolar. It's a pure covalent. Okay. Calculate the wavelength of a baseball. Mass is 155 grams, moving at 25.3 meters per second. Is the wavelength visible to the human eye? Okay, so this is interesting. So we have the DeBroglie wavelength equation, which is given. So our wavelength equals h, which is 6.626 times 10 to the negative 34, and that's in joule seconds, times our mass, which is 155, times our velocity, which is 25 meters per second, so 25.3. And this mass should be in kilojoule, or it should be in kilograms. So it should be like that. So I'm not going to do. I don't know what the answer is for that. You guys can tell me what the answer is for that. And you don't even need to know if it's visible to the human eye or not, because all the answers are different. So whatever you get there for meters, we'll give you the answer. And also, they answer the question in the chat in the meantime. For smallest dipole, it basically means which one's the least polar. So a dipole like HF has a huge dipole. That means fluorine is a lot more electronegative and has a partial negative charge. It will pull the electrons closer to it in a covalent bond. Hydrogen has a low electronegativity, so it'll be partial positive. So it's saying which one of these molecules has the least difference in electronegativity. You can determine that from the trend by looking at the table. And since H2 is a pure covalent, it has no electronegativity difference at all. That's the best answer. All right, anything for number 25? Oh, 18. That was the question. So it's the same, so for 25, for 18, it's the same period. That's where they have their valence shells in the same energy level. That's what we're getting at. All right, for number 24, 25, does anyone have the answer? No? Okay, well, I'll leave it there for now, and we'll go on to number 20. What we got? All right, we'll go back to 18 afterwards. So hold on to your questions for 18. All right, so as you're figuring out 20, so anything for 25, hold on, let me look at the chat again. B, do we have B? Anybody else can confirm? All right, I'll circle B for now. I got D. Okay, so we have either B or D. I'll leave it there for now, and then we'll go on to the next one. And please answer it though. So D. Okay, so you have multiple D. So I'll put D. Okay. So what's the hybridization of iodine in an IF4 minus? This is a good one. So again, iodine is going to be the central atom, right? Because you have 4 fluorines around it. So iodine is going to have 1, 2, 3, 4, 5, 6, 7. And you're right, Nick. There are 2 number 25s. So we are doing the second number 25. And now when you think you got B, well, let's see. So we have 4 fluorines. There's 1 fluorine, 2 fluorine, 3 fluorine, 4 fluorine, and there's also a minus. So we can add another electron to the central atom to make sure there's pairs. So we have 4 bonds and 2 lone pairs. So this means our hybridization is 1, 2, 3, 4. So hybridization is directly associated with electron groups or the steric number. So the steric number, since we have 4 bonds and 2 lone pairs, is going to be 6. If we have a steric number of 6, it is D2sp3. So C is your answer for that. D2sp3. Okay. Next, so place the following in order of increasing magnitude, decreasing magnitude of lattice energy. So if you have the highest lattice energy, it's going to be the strongest bond. So highest lattice energy, meaning it's going to have a stronger charges. So here we have, these are all +1 -2s. So we have to kind of break it down a little bit. So for sodium and potassium, sodium is smaller than potassium, meaning smaller means it's stronger. It'll be closer to the oxygen. So Na2O will be stronger than K2O. And then rubidium is even lower than potassium, and sulfur is bigger than oxygen. So that will be further apart as well. So the weakest lattice energy will be rubidium sulfide. So Rb2s. So it'll be in the order of Na, then potassium, then rubidium. So E is going to be your answer. All right, number 27, which of the following visible colors has the highest frequency? For those in my class, we talked about this a lot. Violet and blues are going to have the highest frequency. That's why they hurt your eyes the most. And that's why we have blue light filters for different electronic devices to help you go to sleep better and to not hurt your eyes, because those blues and violets and pinks and not pinks, but purples are going to be higher frequency and they produce more energy. So blue. And it's in the order of Roy G. Biv, from lowest energy to highest. Roy G. Biv. Not Biv. Biv. All right, so which of the following is a possible set of quantum numbers for a 4D orbital? So for 4D, n equals 4, L equals 2. Since L equals 0 is the S, L equals 1 is P, L equals 2 is D. So we need that as the quantum numbers. So automatically A is not correct, D is not correct, and E is not correct. And we need our ML. Our ML value could either be -2, -1, 0, 1, or 2. So it looks like C is also out because ML is equal to 4 here. So B is our answer. All right, 2 more, then we're done, and then we'll go back to these questions that we all have questions on. So how many non-bonding lone pairs are in the iodine for IBr3? So another Lewis structure that's unconventional. It's good that we do this one. So 1, 2, 3, 4, 5, 6, 7. We have 3 bromines. So we have 1 bromine bound there, 1 bromine bound here, and another bromine bound here. We're going to have 2 lone pairs and 3 bonded pairs. So how many non-bonding or lone pairs? We have 2 lone pairs. Now, what is the shape of this? That's another good question we could ask. The molecular and electron geometry. So to clean it up, we'll have it like this. Br, Br, and Br. So this will actually be, if I'm not mistaken, this will be T-shaped because you'll have the 2 lone pairs and your steric number is going to be 5. Your hybridization on the iodine will be DSP3. And your electron geometry would be trigonal bipyramidal because this is the steric number of 5. So we can tell a lot from just knowing the steric number. Okay, next. Number 30, which sequence does not correctly arrange the elements in order of increasing electron affinity? So I wrote the electron affinity, or I wrote the, I pasted the periodic table below here. So electron affinity increases kind of like ionization energy from the left to the right and going from down to up. So top right is going to be the highest electron affinity, meaning it wants electrons the most. And it releases energy. So these are negatives, right? It releases energy when electrons are gained, meaning it gets more stable. So again, which sequence does not correctly arrange them in order of increasing energy released, right? Increasing energy released. So going from cesium, potassium. So cesium is down here, potassium, sodium, lithium. This is in order of increasing electron affinity. So that is incorrect. So this one is correctly sequenced. So neon, lithium. So neon goes, and then lithium, oxygen, and chlorine. That one is incorrect. But we'll go to the other one. We'll go to C, D, and E first, and we'll explain why. So for C, magnesium. Where's magnesium? Right here. Silicon, right here. Phosphorus, sulfur. These are in order of increasing electron affinity because as you add more electrons to get closer to the octet, the more stable the element will get once it gets another electron. So as you go from magnesium to the right, the more you gain electrons, the more stable it'll get, and the more energy will be released as it gets more stable. So C is correct. C is a correct sequence. D, same thing, beryllium, boron, oxygen, fluorine, same kind of concept. Well, actually, wait, B might not be correct. B might not be the incorrect one. So let's look at B again. So B, we have neon. So neon, has a very low electron affinity because it doesn't want an electron. So it's not really going to release much energy at all. It's actually going to gain energy. To force an electron onto it, it will require energy because it's stable. So it's going to have a very low electron affinity. Lithium can gain an electron pretty easily because it's lithium. So it can go from +1 and then gain one, at least easier than neon. Oxygen can gain one pretty easily as well, so it'll release a lot of energy and become more stable when it does. Chlorine, even better. So chlorine can gain one electron and become a noble gas configuration, which will release a lot of energy because it's happy. So in that case, this is actually a correct sequence. But for E, this is incorrect because nitrogen, so if you go in the order of nitrogen, carbon actually releases is less electron affinity than nitrogen. Then it says oxygen and fluorine. So it goes from here to here to here to here. So that's not a correct sequence of increasing electron affinity. So that's why E would be the incorrect sequence. I will answer questions now. So I know, let's go back to, I think 18 was a big problem. So there's a lot of questions about it. So number 18, which of the following has their valence electrons in the same shell? What this means, same shell, that means the principal energy level N is the same. So cesium, bismuth, and astenine. Let's go back to here. So cesium, see, look, cesium, bismuth is right here, astenine. These are all in the same level. Now, ignoring the D block, because the D block, even if it is in the same level, we know that D lags one behind. So this goes from 6s to 5d to 6p. But if we're comparing those three elements, the valence electrons are located in 6s and in 6p. So they are on the same energy level. Okay, any other questions? I know there was a few more.
Can you go over the question with the lattice energy and like use the periodic table to explain? It's kind of hard for me to understand it.
This one, 26?
That's
Okay, so we are comparing, so there's two things that determine the lattice energy. One is the charges. The stronger charges, meaning that means the stronger bond. The stronger bond, that means more energy is required to break the lattice, or the higher lattice energy. In this case, the charges are all the same. They are all consisted of +1 ions and -2 cation. +1 cation, -2 anion. So we have to look at the second factor. The second factor is the size, atomic radius. The larger the ionic bond, the weaker it is, because the radius will be far apart. There'll be a larger radius. And we know this because the lattice energy is equal to Q1 times Q2, which is the charge of the cation, times the charge of the anion, divided by R. So the larger the R, the lower the lattice energy. So we're looking for the biggest radius to have the lowest lattice energy. And rubidium and sulfur, rubidium is low on the periodic table, so it's going to have a large size. Sulfur is lower than oxygen, so it's going to have a larger size than oxygen. Meanwhile, so that's going to be the largest radius.
Could you use the
Oh,
periodic
yeah.
table to show that?
Exactly. Yeah. So let's take a look. So we look at where we at? So rubidium's right here. Sulfur's right here. So sulfur is bigger than oxygen, and rubidium is bigger than both potassium and sodium. That's why rubidium and sulfur make the largest bond. Then the other two are to compare are sodium and oxygen, and also potassium and oxygen. So potassium is lower down the table, meaning it's bigger because it has one more principal energy level. So potassium and oxygen together will be bigger than sodium and oxygen. That's why it's in that order, sodium and oxygen being the strongest. So, and then potassium and oxygen being the second strongest, or sorry, and being the second weakest, or the second strongest, and then cesium and sulfur being the weakest. Or sorry, rubidium and sulfur being the weakest. Sorry. Does that make a little bit more sense now?
Yeah, the thing is, I was absent when my professor went over the lattice energy. So
Okay. I definitely recommend, let me think. This is chapter 11? Is this chapter 11 or 10? No, 10.
That's the problem. It doesn't specify. I've been on like all the slides, and it's kind of hard to just find it with that much information.
Hold on. So let's end the recording. Let's figure this out for you. All right.